for this presentation. Thank you.
Thank you. So first, Moyen, good morning, everyone. I'd first like to thank the organizers for having me here. It's a great opportunity, and so far it's been really fun being here in Luxembourg. So yeah, as mentioned, how do I turn this on? Oh, turn the projector on. Just have the pointer on. Oh, okay. Thank you. So thank you for Nigel for explaining what a scanning transmission electron microscope is. That really helps me out. Don't have to do all the basics, so we can focus on what's important for me, which is scan dynamics, which is talking about how we actually are acquiring our images, why that matters, and especially why that matters when we're talking about in a subsampled framework. So this is for doing compressive sensing and kind of the considerations we need to make for this compressed imaging style. So first, just a very quick bit on scanning transmission electron microscopy. So this is a scanning imaging format, as you may be aware, where we're using a focus probe of electrons to scan a sample, and then we're collecting various signals depending on our application to form images. Nigel already showed some pictures, but this is what a STEM might look like. This is the one that we have at Liverpool at the moment. We're getting a nice fancy one this summer, so that'll be very, very fun. But yes, so we're acquiring a signal at a set of locations and then forming images from them. So this is a nice little image of silicon dumbbells, which is standard sample for use in electron microscopy for high resolution kind of alignment and things like that. And as Nigel already said, again, making my slides redundant, we can do measurements at the picometer scale. So in this case, it's 136 picometers, 1.36 angstroms. And this is fairly routine for modern STEMs. It's a scanning method. So at each pixel in the image, which are typically on the size of 512 by 512 or 1K by 1K images, you can obviously go higher, you can obviously go lower. And we're acquiring it row by row before doing we call a flyback to go to the next row, and then again, going for more rows. So we have a full set of images, and then if you're doing video, you have a frame flyback to go back to the beginning. Now, these images are being continually formed. The beam is always on when we're doing images. We can blank the beam, but generally speaking, usual operation. The electron beam is always exposing sample. We're always collecting scattering data. So it doesn't matter, as previously asked in one of the questions, you're just assuming you know where the probe is. And if the microscope's doing its job right, it should be where the pixel in the scan coordinates says it is, and you form an image with information at that location. Now, there are some issues there because actually, the images aren't perfect. We have lots of instabilities, and so these arise from various different places. So Nigel already mentioned, €1 million to €2 million to build a room for these sorts of microscopes, and even that there's still issues there. You could spend as much money as you like, and you would still get issues like this. Now, the magnitude of that issue obviously will change depending on who you're talking to, what kind of day it is. Is there someone walking in the corridor next to you? Is there a lorry driving on the road outside? All these sorts of things add up. On the other side of that, the voltages on all of the pieces of equipment in the microscope is fluctuating constantly. All of these things add up to these sorts of distortions. And you can see here, it's coming in as these horizontal kind of striations throughout the image. And we don't like that because ultimately it does lead to a resolution degradation. And it's fine when you've got a nice easy sample like this where you can throw a super high power beam at it and you don't care. But when you're wanting to do fast analyses of materials or low dose, these problems get increased ever so often. So as I mentioned, we're doing raster scanning, right? And as you can see in these images, on the left, looks great, no distortions. So even though we're going row by row, we do a flyback and we tell the microscope, okay, we want to wait. Sometimes we can wait up to a millisecond. Now, you've got to remember each of these pixels is being acquired on the microsecond timescale. So waiting a millisecond every line in a 1K by 1K, that's a lot of time that adds up. So we're interested in fast things in microscopes. This is a big limit. So we just say, okay, what happens if we turn that flyback time off? Well, we get distortions in our image. So on this left-hand edge here, you can see this should be flat and straight. But what actually you get is a dip on the left, then a rise out. And that's because, as we said, these images are being formed continually. And this is actually happening as the beam is going on that flyback. You're flying from the right to the left. You're filling in this information, and that's if you rotate the scan, you can see here we have a nice reflection of the image. So this is, again, the beam is moving from the right to the left. It's acquiring data, it's ascribing that data to these locations, because as we said, we're not doing a wait and hold on the flyback because we want to go fast. And we get a reflection in the image. And this is not good. So just some numbers to throw at you. Roughly, it's about a 30 pixel wide distortion band, 10 microseconds per pixel. That means that the time it takes for the beam to move this distance from the right edge to the left edge is about 300 microseconds. So the microscope gets told to wait somewhere between 500 microseconds and a millisecond. That means we don't see these distortions. And that's what they do in this case. So the reason why you get here is because by the time that the microscope started, you've got a nice continually formed image. Now, the problem here is that you don't have any control over this. This is all proprietary. This is done by whoever is doing your scan control through your microscope. This could be the manufacturer. It could be some other third party. Typically, people use third parties all the time. And so you don't really have any control till you start turning things off. And that's when we're looking at this. So we want the most control when we're doing our scanning because we want to know what actually happens. And yeah, just to validate this, this is what that distortion band on the left looks like. If we just, invert it, rotate it around, we get a nice image. So the reason why this is important and interesting to us is actually we can use this macro scale information to determine what's happening on the pixel to pixel scale, because it's the same process. We're just telling the beam to move to a coordinate, can analyze the distortions at this macro scale, which is a bit easy to digest, and use this to inform kind of our model about what's happening. And as you move away from raster scanning, which is, as we said, what the microscopes are built for, things start to get weird. So we don't want the flyback, we want to go fast. So we can do a snake scan or serpentine scan where you go left to right, then right to left, then left to right on each row. But as you can see, we're getting this kind of, we call it a registration issue, where actually you're getting two images which are offset by some amount. And this is based on your dwell time. This is naturally a problem. There are ways that you can fix this because it's relatively simple. The problem is that this distortion is nonlinear across the image. So on the left-hand edge versus in the middle, you're going to get different amounts of distortions. We don't show it here. So that's something that you need to take into consideration, and people do that. That's a fine way of avoiding the flyback. Other ones, we can do a scan on a Hilbert curve, and we see a resolution degradation. We see the sharpness in the edge of these gold balls, which again, a normal standard sample for STEM, as the sharpness has been lost. And we want to know why. In theory, if we're telling the probe to go to a location and it goes to that location and we acquire data there for a set amount of time, you would think it wouldn't matter what order that the probe is moving in. But it turns out it does matter. Same here, we can go even further. We can try this one, which is a Z-order curve and following a scan on that. So we thought, okay, we want to know what's going on here. We want to try and do some modeling to see if we can validate it. So we take some naive assumptions about what our scan coils are like. This is a double deflector electromagnetic scan coil. And we model it as a double harmonic oscillator. So the blue line here is the first of the two harmonic oscillators, which follow this form of the equation on the left. And then we have the second oscillator, which follows the blue line as the input. And we can feed it just a step response, and we can look at it, and that's sort of what this is. So we've developed this model where we take this equation, we have this double harmonic oscillator model, and then we can feed it in a scan coordinate and see, okay, actually, if these are the step function responses that we're expecting, what's the actual response to that, and what does that look like? So this is what a flyback on a small raster scan would look like. You can see along the line, it looks pretty good. We have decent registration. Sorry, this is hard for me to control. We get decent registration across the line, and then on the flyback, we have this massive overshoot, and then a kind of a wobbling back onto the line. And then again, as the line continues, things stabilize again. So this is why raster scanning is good, right? You have one negative event per line, generally, and once that's over, your image looks nice. And this is the industry standard for a good reason, and we'll see why going forward. So yeah, on here, yellow spots is where we tell the beam to go to. The white locations are the actual locations of the beam time result. So we can put in whatever scan coordinates we want, and so we can show all of these different ones. Yeah, so here's the snake scan, the Hilbert scan, and the Z-order scan, and we see some interesting things. So yeah, snake scan initially looks good. We have good coherence between our scan positions and where the beam supposedly goes. Again, you still have this kind of like oscillating effect on the row change, but not as bad as the raster, so we're okay there. But again, we have this registration issue still. where when we're traveling left, the beam lags behind the mask, the scan coordinate, and when we're traveling to the opposite direction, it lags in the other direction. Hilbert curve, the beam never goes in straight lines, which I think is really interesting. And that's why we're getting this like distortion on the edges of these particles where we're never actually where we think we are. And actually, as you go to faster scanning, this just gets worse. And then Z order again, looking at the construction of this curve, it's all over the place. You know, you have these large inhomogeneous jumps, and this is not good for image quality generally. So just to go into a bit more detail before we go more forward, we have this flyback issue on raster scanning, and we can now do some analysis on this to kind of use this model just to check, does this make sense? Are our assumptions sort of correct? So we can look at what the deviation of the probe is versus the scan coordinates, and we can see when we're popping it along the line, yep, we have pretty low errors here. The probe is somewhat close to the actual location we think it is, and then we get a big distortion on the flyback. We get this big error, which means that when we're assigning detector flux, electron flux from the microscope to these pixels, we're assigning the incorrect information. On the micro scale, that is also sort of happening on the pixel to pixel scale as well. So your probe isn't exactly where you think it is. It's some path between where it began and where it ended. And this depends on characteristics of your scan coils. But we don't have to show it as a graph. We can show it as kind of just a plot like this, where for each pixel in this image, we're showing what the distortion was from that pixel, from the one before it. And yet, raster scan looks nice. We have this strong left edge where the distortion is poor. And then the actual rest of the field of view, it's nice and consistent. And we get a mean of about 1. So it says, hold on, that means that our probe is 1 pixel out of position all the time. Well, no, if you exclude the flyback, actually during the regular section of the image over on this right section, it's pretty good, 0.3 out with a very low variance, which makes sense considering that we're looking at this nice flat region. And this is why raster scan images look good, is because you have a very consistent deviation of the probe from the scan coordinates. So you don't actually care that the beam is on the scan coordinate that you posit. You care that it's always the same amount out of phase, right? So we can look at the other type of scans. Again, serpentine scan looks great. Very low mean, very low variance, no problems there. Hilbert scan, a little bit higher mean. Variance, not bad, still higher than these other two, but that's okay. Z order scan, all over the shop. Now, one of the reasons why we posit that these two scans, the Hilbert scan and Z order scan, are poor is actually not because these means are bad or anything, but because they're inconsistent across the field of view. You can see that there's speckling in this image, and that means that depending on which pixel you're registering at, you can get a different amount of distortion, and that's going to lead to a degradation in your image quality. Same for Z order scanning. So how can we take this a bit further? Well, we wanted to include an image kind of simulator to this model so that instead of just looking at distortion values, we can actually look at distortions in the image. So we take just a continuous function like this and we discretize it. And so this is what that function would look like with a perfect scan. Yeah, so it's just balls, as I just said, all high resolution STEM images are just balls on black. So we're fine with this as an analog, and it's discretized because we're forming a discretized image. So in this case, we're saying the probe is at this position, and it is, and we're happy, and this is the sort of image that we get. We discretize it. But what if we actually take the scan model into account? You can see here, first model, we would just acquire a intensity value at the red marks, and that was it. But actually, in our developed image simulation with the scan modeling, we're taking the beam along some model pathway, and then it's the flux from that path that is being applied to the coordinate that we're scanning to. And then so this is what the simulator looks like. So the blue dot, if you can see that, is the idealized scan coordinate, and then the red pathway is the actual path of the beam as it moved. And so what that looks like is, we get a scan distortion on the left-hand edge, somewhat similar to what we see in our experimental images. We have a downward dip followed by an upward dip, all great. Serpentine scans, exactly the same problem that we see in the experimental images, where we have a registration issue going from left to right and then from right to left. Hilbert scan, degradation in quality, as expected. Z order scan, even worse. And then along the bottom here, we can show the scan paths of these that were used to form these images. Well, our examples therein. So so the raster scan, you can see there's a little bit of a fluctuation in the y-axis. We're off the path a little bit. which is, not totally unexpected, but that's okay. 17, a little bit worse. We're having this rounding effect as we go from left to right and right to left. Hilbert way off the mark, way off the mark. The beam almost never actually goes to where we think it is. It's never close. Same for Z order. It doesn't even attempt to follow the curve because we're scanning too fast. If we increase the scan time, something like this, we get a bit more cohesion. And this is also true. You can keep going further. You can increase the dwell times as far as you like, and eventually you do get full coherence. Problem with that is obviously you're going slow with a longer dwell time. Nobody wants that. So obviously we're talking about compressive sensing here, and all of the problems that have been mentioned so far only get worse when you start talking about subsampling, because all of a sudden you have non-regular scans generally. They're not well structured, or they can be structured, obviously, depending on your application. But for us, we try to use non-structured scans. And so, yeah, so this is the idealized case that was found for using with a scan coil. This was just found by happenstance, just by thinking, okay, how can we modify a raster scan? Raster scans do well. And so what they do a continuous movement in the X direction and then a random perturbation by 1 pixel in the Y direction. And we can get experimental images out. And again, we use BPFA to do our reconstructions, but that's not the focus of this talk. And this is pretty decent for STEM. So the experimental inpainted data that Nigel showed earlier was also done using this line hop kind of method, and it's pretty well tested. And so we did some simulations, and we can say, oh, actually, okay, yeah, this makes sense. This is a valid answer. We actually get decent cohesion between the scan coordinates and the beam. So we obviously can go into a lot more detail on why this is the case at a later date. But right now we can validate that, okay, the choices made arbitrarily were actually quite fortunate and very well chosen. They did their due diligence. But we can look at other subsample scans. So here's the other 4. We've got the modified raster scan, modified raster with a snake variant, and then subsampled Hilbert. So this is just by doing a coin flip to say whether or not a pixel in the Hilbert curve should be included. Same for the Z order. And yeah, and we get interesting results. Line hop scan looks good. Snake, not so good. We're actually getting artifacts here in the image as well. So this is the mask is being overlearned by the inpainting, the dictionary learning inpainting algorithm. So we're getting a checkerboarding effect in our images, as well as obviously a quality degradation. Hilbert scanning, yep, exactly what we see again from the regular full sampling. We're getting a quality loss. We're getting a degradation of resolution. Same for Z order. And again, this is all because the beam actually isn't where we hope it is. Going further, just looking at some other subsampling methods that were tested. Some of these are a little bit better. Lane constrained random. So this is like line hop, but without the constraint of plus or minus 1. We define a lane and we can choose any of the pixels moving left to right. This one's pretty good. It's about comparable to line hop, but the mask design is a bit more favorable for the dictionary learning because you don't have this as tight a constraint. Snake variant, again, doesn't work. You're getting elongation in this x-axis, which is unfavorable. Jittering, so we define a 2x2 for 25%, a 2x2 box, and only one of the pixels are being sampled in that box, and then we're doing that in a raster scan across the whole image, and then jittering with a snake. Again, snake scans don't work because we have this registration issue. That's not to say these can't be solved. It can be solved, but not without further treatment. So what can we do? Could we do some kind of rectification method to solve this problem? Well, obviously this is a simulator, so we have access to all of the perfect information in the system. So this will be our kind of original image on the left. Here we have what we call a rectified image. So this is, instead of applying it to the scan coordinate, if we can find a way to measure the actual location of the probe, apply the detector flux to that location instead. Looks great. We have no physical deformation of the material. We just have some issues with image contrast. And that's because actually, if you look here, the probe is spending more time in certain locations than others. So you're getting more flux in those locations just by the fact that the probe is there. However, if you know both of these pieces of information, the kind of where the flux should have been applied and the time spent at that location, you can normalize it. You can get a contrast-free, no contrast variation, distortion-free image. Now, the question is obviously, is this realistic? Can we actually measure the probe location? We don't know that right now. There's been some work done in the past where they seemed to have been able to. Unfortunately, when reached out for comment, they wouldn't give us one. So this is something that's ongoing here. The reason why this is very important is because it absolutely frees up what you can do. You don't have to worry about hysteresis quite as much if you have all this information. And for instance, you can see here, we have a simulation of a random scan, which historically for our applications does not work. But if we apply the electron flux to the actual location that the probe was instead of the scan coordinates, we can get the structure is retained again. And if we know the density of the probe locations, we can rectify a nice normalized image out. So this is also important if you're not concerned about subsampling, obviously, but you're just concerned about faster scanning, which the distortions get even worse. In fact, actually, there is a limit to how fast you can scan in STEM, never minding flyback distortions. So if your probe can't keep up with the rate that you're changing the scan coordinates, you get these distortions here, which you can see in the rectified image. It's actually because that's where the probe spent nearly all the time. So this is a distortion you're getting because the probe isn't anywhere near where you're thinking. And you might see this and think, oh, it doesn't look bad, but you're nowhere near where you think. This is like a false reading that you're getting. But again, if you can find a way to measure this information, you can normalize your images, and in theory, you can get something cohesive out of it. Then the worry gets moved elsewhere. So say you don't care about hysteresis, you still need to care about the structure of your scan, because in this regard, you want to try and do this fast random scan. You don't cover the field of view because, as we said, the probe never reaches the scan coordinate. So this is a 100% scan. There's no subsampling here. In theory, the probe should visit every coordinate, but if you're trying to move too fast, you're never going to reach those locations. This is another thing to worry about. The point being here, if you can access these probe locations, you can be really crafty in how you can form subsampled images. You can imagine instead of doing something like this, where we're visiting every location, we actually scribe lines through the image as a function of the probe moving. And that's how we form our subsampled images rather than visiting a subset of pixels. We think about the pathway of the probe as opposed to the fixed locations of the probe on the discretized grid. So just for some closing thoughts, and just to show you, this is what random scanning would look like in a real STEM. This is why we get noisy images out, because the blue location, the proposed scan coordinate, and that's the beam in red. The beam never approaches the coordinate in any regard. Some closing thoughts on the matter. Obviously, we had a naive oscillator for our model. We want to kind of know, is it accurate? We're going to try and find that out. Can we update it? Are there other applications, other scanning methods where we can extend this model for? Are there other things that have the same problem? We know scanning transmission electron microscope and scanning electron microscopes very similar in terms of scan coil design, but are there others that we can think about? The noise model, we have, our electron flux detector is perfect. It gets everything 100% right. How does changing your mask matter when you have a more realistic scattering image simulator? And can we incorporate noise and things like that into it? So we talk about instabilities in the scan, but what about the other ones that I mentioned? Drift of the sample is a massive, massive limitation in STEM. Is there something to say about how the mass design should be reflected when we have drift in the problem? But also things like vibrations, people talking in the room matters, people coughing, things like that. And then voltage instabilities, temperature instabilities, these sorts of things. And can we incorporate this directly into our acquisition platform? So can we predefine on our microscope how things are going to look, and can we update our live acquisition with information from models like this? These are all open questions. If anyone has any insights of it, we'd love to talk about it, because this is relatively early in the development of this project. So there we go. So, yeah, thank you very much.
Thank you, Daniel. So we have time for questions. So is there any question in the room or online?
I have a quick question. I really liked your illustrations of different visualization. Could you explain again, when you did this snake scan, the shift registration issue, what was it? I couldn't get it exactly from the illustration of the thing.
Okay. Yeah, so if you imagine, I'll do it in my hands because it's easier. This is your scan coordinate, and we're treating it like a step function, moving like this. Actually, the beam is probably somewhere just behind, okay? So it's not directly incident and it's not linearly behind either. It probably looks like this. So you can imagine there that when you're traveling from left to right, you're always slightly off kilter. Now, when you're traveling right from left, you're off in the other direction. And so essentially you're getting two images that are off by some phase amount. And it's a non-linear phase amount across the image platform. So on the left edges, it's different to in the middle. And so you have to take that into account if you do any fixes. There is a paper that does that though. So there is some work on that regard because we're looking for solutions to this timing restraint on raster scanning. Yeah.
Any other question? I may have one question. So related to when you, in the practical use of the model you presented, you say that you can incorporate. Would be nice to incorporate that into a microscope. It's more to help to control more precisely the probe, or it's like like to estimate the true path after all. When the acquisition has been done, it's like to correct. To estimate what was the real path, or it's to try to better monitor the.
Yeah. So the other side here is if you can measure the probe location, the actual location. This model is just some things like this are just good for helping you before you go to the microscope. If you're doing iterative design where you don't want to have to get on a microscope, which is an expensive endeavor. 20,000 a day, you can do your testing here if you have a good model. The other side of it is if we can't measure the probe location, which we don't know right now, models like this will have to be used to inform kind of that missing information. If you have a good estimate of your microscope, if your model is well representative, you might not need to do the measurement, especially if it's not possible. So that's how we posit that this is going to go. Because the problem being, you can measure the voltage on the scan coils, but how are you sure, does that actually correlate to where the probe is within that? How accurate is that measurement? How fast can you do that measurement? These are all questions that we need to get a grip on. The only problem is the manufacturers it's really black box about this. They really don't like you prodding and poking because unfortunately you'll unravel the web that they have spun to get images that look good. Like we know that they're doing things behind the scenes that they don't tell us about because obviously they want the edge on the competition. It's just a question of can we disable all of that stuff, get the real data, get as much info as possible. And so we're excited about how that's going to go if we can get the manufacturers on board, which it looks like we'll be able to. So.
Thank you. Yeah.
Thank you. Naive question. So is it possible to have a super well-known sample such that if you know it very well, like for instance, a sinusoid pattern or okay, of course, it won't be like that for atomic structures, but let's dream of that, so that you can recover afterwards the location of the probes by the intensity that has been recorded at that location. Is it something possible or that
absolutely. Yeah. That's something that's the next step, most likely, is getting something in the image simulator that looks realistic, find the analog within the actual microscope, put A to B to make sure all the parameters are the same, scales are the same, and all these sorts of things, and then see how well they match. Then we can iterate on the model, see if that lines up. Maybe it's completely wrong. Maybe it's not only a little bit far away, and then we can see. The next step from there, obviously, is okay. If we know parameters about a microscope, we've got a decent model. How can we change things fundamentally within the model that could reflect actual changes on the microscope to make it more efficient? So these are things like we know that there are ways that you can deal with moving between certain positions in your scan coordinate maps that aren't as simple as a step function, which may give you increased stability. Some people, rather than do a flat step function, they do like a sinusoidal approach. Some people do linear approaches. And again, this is all hidden within the black box of the microscope. They won't tell you how they do it. So these are other things to consider is, would a hardware redesign at this point be beneficial? And how can we predict what that hardware redesign should look like? Because none of the hardware's changed since the 70s either. That's the other thing. They have been using this since STEM was made. And they've had no reason to iterate because it's done the job. We're getting picometer resolution. I think the world record is 30 picometer, atomic distances being resolved, which is incredible. but the question being that only works in a very specific set of circumstances. We're looking at something now when we're talking about subsampling that is a lot more flexible. And so our microscope needs to be able to handle that flexibility. So that's the way that we're moving.
Okay, thank you.
So I think we keep the other question for the break. So thanks again, Daniel, for this very nice presentation, and we go to the next talk.